Okay, now let me present this example. Okay, we have been discussing main topics related with voltage transformers. Something that is extremely important is what is the connection used between the voltage transformers. I mean, what is the topology? In a three-phase system, we have three voltages. And we typically use we want to know the three voltage. Okay, however, with voltage transformers we have different topologies that we can use. In a minute I will present the two most used topologies, but the idea of this exercise is that you can be able to identify the depending of the topology used to connecting the voltage transformers, you are affecting the measurement. And as protection engineer, you must be aware what is the connection that you are using. And if the protective relay has not mechanism to correct automatically the connection, it's your job to make the appropriate changes that you need in order to compensate the topology. Okay. This example is extremely simple. There is in this case, we are using a three-phase system. There is a phase A, B, and C. And then here we have three voltage transformers. And these three voltage transformers, you can see using the topology is delta connected, yes, and secondary is a delta connection also. The secondary of those three voltage transformers are connected to a delta connected burden. Okay, we have here delta on the primary, delta secondary, delta at the burden. Okay. Here there is another connection. Here again we have a three-phase system, A, B, C. And then we have, instead of using a three-phase connection, this is what we call delta open connection. Delta open connection, we use only two voltage transformers, one of them connected between phase A and B, A and C, and then BC, okay? You can see delta connection at the primary, delta connection at the secondary, and then we have here a three-phase delta burden, okay? The data for the leakage impedance is known. We know that the burden is mainly a resistor, 50 ohms. And these voltage transformers, they are connected to a primary voltage of 69 kV. And of course, the secondary voltage is 120 volts, okay? Let me start with the first connection. In the first connection, it's extremely simple to see. We have delta at the primary, delta at the secondary, delta at the burden, okay? As you can see, the terminals A and B, they are marked here, A and B. But the terminals A and B, you can see there is a voltage drop across the impedance, the burden, okay? Using Ohm's law, it's very simple to see that this current is the voltage divided by the impedance, okay? However, this voltage here is also the product, or can be calculated using Kirchhoff voltage law in this loop. If we use Kirchhoff voltage law in this loop, it's very simple to see that we can get again the voltage in terms of the leakage impedance and the series current moving on the secondary of this transformer. Okay, now it's just basic mathematics. What is the idea? The idea is we have here one side of the equation that we have BAB, and the other equation, the other side of the equation, we have BAB0. VAB0 is the voltage, internal voltage that is coming from the primary, okay? If you look over here, if we put together all the numbers, what we are getting here is that the voltage that we are receiving between A and B is not necessarily the voltage that is coming from the primary. I mean, if this relation is 1-to-1, we can say, okay, the voltage across the terminal at the secondary of this voltage transformer is 100% the same voltage that we are getting on the primary. I mean, just a 100% reproduction. However, I don't know if you realize, but here we have now what we call a correction factor, a ratio correction factor. What does mean the ratio correction factor? That means that the voltage that we are getting, because the connection of those transformers is different to the voltage that is connected, that is supposed to be measured, okay? In this case, it's 0.97 and a 5.6 degree phase shift, okay? But the situation is more interesting when we look around this kind of connection. The open delta connection, we save money because you use only two voltage transformers, and they are two voltage transformer connected to the three-phase system, 69 kV. But the secondary, we are installing a three-phase burden, phase A, B, and C using delta connection, okay? Delta connection, they still using the properties for the three-phase systems. That means that the three voltage should be 0. But more important is, right now, let's calculate the voltage AB and the voltage ABC, okay? Here, there is expression for the voltage AB, then the voltage expression for BC, then let me express the current that is moving on the terminals here, current A and current B, okay? Now what we want to do is convert those expressions in order to see what is the relationship between this voltage here inside the voltage transformer and this voltage at the terminal of the burden, okay? Now, using just the basic mathematics and using the properties, the relationship between phase and line voltages, what is very interesting here is that finally we can calculate the voltage CA and the voltage CA0. There is again a relationship, and this number is different to 0. In this case, the number is 1.017. What is the idea? Well, the idea is that this number is what you need to multiply the voltage that you are getting in the secondary of your voltage transformer in order to get the right value that you are measuring, okay? It's very important that you be aware that the delta connection introduces a very different phase angle in the three voltages. As a consequence, you must be aware about that phase shift in order to correct your measurements for positive, negative, and 0 sequence, okay? What is the good and bad news? The bad news is, well, here you can use very basic mathematics, circuit analysis, and you can calculate those transformer ratio corrections. But the good news, in real life, many modern transformers, especially digital and numeric transformers, some of them, they have a software that is already making those calculations and correction for you. As a consequence, when you are setting the protection, what you need to do is select this option, and automatically positive, negative, and 0 sequence will be corrected depending on the connection, delta connection or open delta connection, okay? Okay, well, we are almost near to close this presentation, this class today. I would like to spend a few slides talking about non-conventional instrument transformers. Okay, in the previous session, we talked about the conventional or traditional current transformers. Then we talk about the different kind of voltage transformers, and what I will do now is talk about some non-conventional instrument transformer. Few of my colleagues from the industry, protection engineers in the field, all of them agree that the technology is changing. The need for faster and more reliable and more accurate protections is creating changes. Okay, it's creating changes. We are moving to a fully digital substation. Full digital substation means not only monitoring, is also including measurements. Okay. And to be honest, everything in this digital direction is what is helping and making so exciting the use of IC 61850. Okay, I must be honest. There are a new traducers that you can find. This section is not intended to be a full summary. It's just a very, very basic introduction overview in order that students know that there are new technologies coming in. Well, some of them, they have probably a decade in the market, but you must be aware of them because it's very, very important, okay? Those new transducers, they are mainly impacting what is voltage and current measurements. Okay, they are something called magneto-optic current transducers. They are something called electro-optic voltage transducers. They are Rogowski coil, and there are some other technologies. But what we are looking for is the following. Okay. Traditional relays, they use traditional CT and VT. CT and VT, okay, they are very good because they provide the galvanic isolation. However, there is an issue because you are exposing your signals to some noise, and there are many effects related with the transformer per se. I mean, saturations. There are many things affecting. However, if we can use some technologies that they already provide the signals in the digital world, that will be a massive step forward. And those devices based on optical metering units, they are doing so. What is the advantage? The advantage is those devices, they are more linear or totally linear, and as a consequence, they have a very high accuracy in a very wide range. Okay, you can spend a lot of money in a very expensive CT, traditional CT, but the magnetic core, there is a natural consequence that there is saturation. You must spend a lot of money in order to put that saturation very, very high, but that is a possibility. With those new technologies, is almost linear for a very wide dynamic range, okay? Also, another thing related with the traditional CT and VT is the dynamic response. Because during transients, you have capacitance, you have inductance, and as a consequence, they are transients that they are intrinsic to the system. With optical based metering, okay, you have again some dynamic, but this is so fast that the affecting on the signal that you are interested in is almost is almost zero. Okay, those devices also they save time, they save weight, they integrate with the power apparatus. I mean, some of those because they are if you are using fiber optic, they offer some insulation, and as consequence, you can integrate the device and the transmission communication transmission inside the device. Okay. In some places, it can be useful also to use. To use with the traditional measurement system. Okay, what is the disadvantage? Okay, those digital devices, those optical sensors, they have a problem. They produce very low power. Okay, we are talking about milliwatts. If we are talking about distance of 50 meters or something like that, probably we are safe. But in a big substation, one of the problems is that probably you will need some power amplifier, and that is where a lot of money is needed. Okay, this technology is coming. I am sure that in few years more and more substations will use this kind of technology. Is already a standard. There is already a standard regarding using this kind of technology. Okay. Another technology that is already in the market is the Rogowski coil. It's basically a coil that is many turns, but at the same time there is no magnetic core. Okay, advantages of this. The advantage of this is mainly because you don't have any metal or iron core. You can put directly into the around the cables, and you can get a measurement. Okay. However, depending of the size of the measurement, the size of this Rogowski coil can increase. Okay, that is probably one of the drawbacks. Also, there are some new equipments that they are coming to the market, and they are using Hall effect sensors. Okay, Hall effect sensors has been used for a while in microelectronics. However, the technology is evolving, and now you can find some big sensors that you can use for relative medium-sized power. Okay, magneto-optical range transducer. They are already in the market. There are few manufacturers offering them, General Electric, ABB, and so on. Basically, they use the Faraday effect. And they use the Faraday effect in order to estimate what is the induction, what is the magnetic field, and from there you can identify or you can calculate the current that is moving inside the measurement device. Okay, they are very good, interesting features here. There is no risk for fires or explosion. Those devices are almost immune for electromagnetic interference. They can work in a very wide frequency range that allow you to have a quality signal, especially for very interesting high frequency phenomenon. Okay. The output is very low. That means that you can connect those devices directly to any digital component. Okay, and also because you don't need any kind of wire conductor, insulation is no a problem with those devices. Okay, I highly suggest, if you have time, that go to General Electric website and have a look on the CTO current transformer and have a bit reading on them. Okay. Finally, the last technology is the electro-optic voltage transducer. Again, we are using principle from physics. In this case, is the Polarity effect. Essentially, what we are doing is using a device that, depending again on the magnetic field and electric field, they produce a signal that is quite correlated with the voltage that is sensing this device. Okay, Interesting thing is they are almost zero electrical interface with the signal from the line. It's extremely fast and working in a very wide range of frequencies. That means allow you to detect many other things that with a classical, with a cheap classical VT is very difficult. Okay. Well, this is just an introduction. I hardly suggest, again, there is a manufacturer, General Electric. They produce the BTO, that is a voltage transformer optical based, and you can have more reading more about those devices. Okay. I would like to close this section saying that in this section, in this class today, we introduce different kind of transductor and the mechanism of transforming voltages and current, okay? We present some of the most important industry standards. We talk about ANSI, IC, and also, thanks to my colleagues in Australia, we also talk about the Australian standard. We discussed just a bit about the importance of the transient response of the current transformer and voltage transformer. However, that is a topic that is beyond the full scope of this. Finally, we discussed the importance of the response on relaying, and new technologies were present here. Okay. Final slide with few references that you can go over there, and also there are many more references included in the document. Please go there and have a proper reading. Okay. It has been a pleasure, this class today, power system protection. We cover conventional instrument transformer and a very short introduction about non-conventional instrument transformers. Non-conventional instrument transformers, they are coming for the needs of a digital substation, and that is coming by the hand of the IEC 61850. I am Francisco Gonzalez. It has been a pleasure. Thank you very much. Please check the repository ResearchGate at GitHub, and thank you very much for listening. Thank you.